Alright, silly people, here's the situation. We're just trying to prove the result of a few integrals, 5 integrals, that Blundell quotes in chapter 5, um, using the definitions of the functions that we're integrating, as well as the results of some table integrals, which I've already written down. Also, by the way, throughout this problem, I'm using a notation where if you ever see an integral that doesn't have bounds on it, that means it's integrating over all space. I just did that to save a little room. Um, so let's get into it. The first one was Vx g v of x dvx. Um, so that's going to be the integral of Vx times the square root of m over 2 pi kbt times exp minus mvx squared over 2 kbt dx. Or no, not dx, dvx. So just looking at this, you can already tell it's of the form of this first table integral here. It's an integral over all space of x exp x squared. So this is equal to 0 already. So Blundell was right on that one. Let's keep going. The next one was 2 times v sub x times g v sub x. Okay, so it's the same one, but multiplied by 2 and with different bounds. I'm going to bring the radical out of the integral first. So like that. And then in the integral we have vx, it's 0 to infinity, exp minus mvx squared over 2 kbt dvx. This is the second table integral that I wrote down, which has the results equal to 1 over 2 c, c being the negative factor inside the exponent. So just, and it shouldn't be equal to 0. So using that, 2 times the radical, and this is going to be 1 over 2c. So 1/2, and then c is 2 times kbt over m. So inverting it, you get that. You get some cancellation. The 2's go away there. And then we can move everything into the radical by squaring the stuff outside. So you'll have m, 4m, kbt squared, t squared, over 2 pi kbt m squared. Simplifying, 4 will go to 2. You end up with an m on bottom and a kbt on top. So 2 kbt over pi m. Just checking that that's what Blundell got. Yeah. Alright. Next one. We're doing vx squared now. Over all space times g v of x. So again, I'm going to go ahead and put the radical outside. M over 2 pi kbt. Integral over all space vx squared times exp minus mvx squared over 2 kbt dvx. Now we're using our third table integral, which has the result, which has the result 1 over 2 times the square root of pi over c cubed. So plugging that in, you will get m over 2 pi kbt times the integral. It's not an integral anymore. It's 1 over 2 square root. Let's move the square root of pi up the top here. And then invert the square root of c cubed. So it's going to be 8 kb cubed t cubed over m cubed. All right. What's cool is that the square root pi goes ahead and gets canceled out. We can move the rest of the, we can combine the radicals. So you'll have 1/2 out front, 8m kb cubed t, that's supposed to be cubed there, t cubed over 2 kbt m cubed. So you'll end up with a 4 kb squared t squared over just m on the bottom, m squared even, m squared. And then you can simplify that, actually do the square root, so it's going to be 2 times kbt over m, and the 2's will cancel out, and you just have kbt over m, which is what Blundell got, so we'll keep going. The next one involves a different integrating function. It's f of v. So this has kind of become a mess. I'm going to go ahead and move this down. In the prefactors on the outside of the integral, and it's from 0 to infinity, we basically have this stuff times, we're integrating v cubed now. So I'll write this as v cubed. And then, so this has a form of this guy that I wrote down. So it's going to have a solution where it's 1 over 2 c squared. So plugging that in, we have 4 root pi m over 2 kbt to the 3/2, and it's 1 over 2 c squared. So we'll put the 1/2 out here and then invert squared c, so 4 kb squared t squared over m squared. Okay. 16 over 8, or 16 over 2 is 8. So we have 8 over root pi. And we can, I'm going to go ahead and call all of this stuff like that. just so we can do a little bit of exponent adding. And then it's kb squared t squared over m squared. 2 minus 3 halves is 1 half. So 8 over 2 is 4. You have 4 over root pi. And you have 1 over root 2. And then you have the square root of kbt up top and m on the bottom. You can throw everything into the one radical. So you have 16 kbt over 2 pi m, and then you can simplify that to be root 8 kbt over pi m. Does that check out? It checks out. Next integral was it's 0 to infinity v squared f of v dv. So we're doing pulling all the prefactors out first. So it's 4 over square root pi m over 2 kbt, 3 halves, and then integral from 0 to infinity v fourth exp minus mv squared over 2 kbt dv. So this is going to be our last table integral that we use, which is going to have a result equal to 3/8 times the square root of pi over c to the 5th, right? So what you're going to end up with is 4 over root pi m over 2 kbt, 3 halves, 3/8, 3 root pi 8ths even, and then the inverse of square root c fifth, so it's going to be 2 to the 5 halves and kb to the 5 halves and t to the 5 halves over m to the 5 halves. All right. These root pi's will cancel out. 12 divided by 8 is, well, it's 6 divided by 4, so 3 halves. Right? Yeah. So 3 halves. And then 5 halves minus 3 halves is just 1. So you have a 2 up top and kb t over m. And then the 2's cancel out, and you just end up with 3 kb t over m. Checks out.